All right, we have finished learning how to do derivatives. We now know how to do the derivative of all sorts of things. And now we're going to start into our applications of derivatives. What do we actually use them to do? We should already know that the derivative is the slope of the tangent line. It's the instantaneous rate of change. It tells you how something is changing. So an equation that has, y equals will be telling you where something is, like at different x's, what's the y value? At different x values, y prime is telling you how is that thing changing, like what's its rate of change right then. And so today we're going to begin a new unit called related rates. And this unit is interesting in that it's got a lot of like real world engineering applications. Honestly, like I didn't use this a ton outside of like engineering classes in college. But it's very important for things like engineering. It is a rather small portion of the AP exam. It's about 8% of the AP exam. And what makes it especially small is that it's not necessary to do the things that are coming later. So there are going to be questions on this unit on the AP exam, for sure, like a few questions on it. But if you, for some reason, like don't do well on this unit, it won't stop you from learning the things that are coming later. Whereas if you don't know how to do like your derivatives mastery quiz and know how to do derivatives, well, you're not going to be able to do a lot of stuff the rest of the year. So this one's kind of a standalone unit, which is interesting. And where it's going to come from is it's going to begin with the idea of implicit differentiation that we did last unit, and it's going to extend it to taking the derivative with respect to time. How do different quantities that are related to each other, how do they work when you see how they're both changing with time? And we'll talk about that in a minute. So start by finding the derivative with respect to x of both sides. You don't need to solve for dy dx. You just need to take the derivative of both sides. So what is d dx? The derivative. This says the derivative with respect to x. I'm going to write that. Derivative with respect to x. And we're going to do it on both sides. So hopefully you found that when you do the derivative of y cubed, you get 3y squared. So 3 times y, we lower the power by 1, but then we need to do the chain rule. The derivative of y squared is y prime. And sometimes for this unit, we're going to be writing 3y squared dy dx sometimes. Sometimes we'll write it like this instead of y prime. But either way is okay. So, we get that plus the derivative of x squared is 2x. And now we don't need to do the chain rule because it was the derivative with respect to x. And the derivative of 3 is 0. And this one has an x in it, so the derivative of sine of x is cosine of x. And hopefully we feel comfortable with this. Although, again, sometimes the y prime in this unit will be rewritten as dy dx. Now, look at this next problem. What about d dt? This is the derivative with respect to t. And so now this is going to act a little bit differently. So the derivative of y cubed is 3y squared times the derivative of the inside function, because it's not d dy, is going to be, I'm going to write dy dt. I'm going to switch over to this way of writing it just for this unit. So 3y squared dy dt plus, all right, now before we were doing the derivative with respect to x, but now the derivative of x squared is going to be 2x, and we have to do the chain rule here because it's not, the derivative of x is not just going to be 1 because we're doing it with respect to time. And it's going to be dx dt. Notice it's d, whatever the variable is with respect to t here. So dy dt, dx dt. The derivative of 3 is still 0. The derivative of sine of x is cosine of x, but now we need to multiply by the derivative of x because it's not the derivative with respect to x, it's the derivative with respect to t. And so we need dx dt, the derivative of x with respect to t. And I'd just like to point out what this means. This is saying that this is about how things are changing. So dy dt is, how is y changing over time? How is x changing over time? And this is a related rate. These rates are related to each other based on what the original function was, and it's going to give us some power to do some things. All right, why don't you guys try this one on your own? This isn't about time. Notice that it's ddm. What is the derivative of both sides here? And we should notice that the derivative of y cubed is 3y squared times dy dm, because that's what we're doing the derivative with respect to, plus 2x dx dm, because we had to do the chain rule here because we aren't doing the derivative with respect to x, we're doing it with respect to m. The derivative of a constant is always 0, and the derivative of sine of x is cosine of x, but we have to do the chain rule because it's not with respect to x, so it's times dx dm. Now I could use y prime here and x prime, but x prime kind of seems a little bit weird, and so we usually are very specific and say dy dm and dx dm when we want to find the relationship between two rates. Try another one on your own here. Hopefully you're feeling kind of okay about this. What's the derivative of both sides? d dt, notice it's d dt here. So the derivative of y cubed is 3y squared times dy dt, plus, now it's the derivative with respect to t of t squared, and that's just 2t. There is no chain rule here because the derivative of t with respect to t is just 1. And what that kind of means is like, hey, if you've got the graph of y equals t, the slope of t with respect to t is 1. Just like the slope of x is 1. So if you're doing it with respect to the variable, there will not be any derivative there. Equals sine of x dx dt. This one we did need the dx dt. This one we needed the dy dt, but because it was the same variable that we were doing the derivative with respect to, we did not need a times dt dt. And we can also think of it as like dt dt kind of would cancel out and just be 1. Okay, ddt of this one. Let's see how you guys do. The derivative with respect to time is usually what ddt means. So the derivative with respect to time of all of this one is a t, so there's not going to be any chain rule stuff here. It's going to be 12t squared. Plus the derivative of cosine of x with respect to time is negative sine of x. I guess I should have just put a minus in front there. Negative sine of x times dx dt, and this would simplify into being a minus if I were going to rewrite it. I'm not sure I will. Minus the derivative of sine of y is cosine of y with respect to t, so I need to do the chain rule, times dy dt, equals the derivative of 20 is 0 because 20 is a constant. Hopefully you're feeling okay about that. And if I were going to rewrite this, I would rewrite this as 12t squared minus sine of x dx dt. And then, minus all this. All right, how about the derivative with respect to t? Again, this is the derivative with respect to time is usually what t will stand for. It's like, how are things changing over time? Which is a very real world thing we want to care about, is like, hey, when stuff is moving, both x and y might be changing. Before we go any further, let me just show you like an example of what we're talking about. Like, let's say there are cars moving, and like there's a car moving this way or something. Well, its x variable is changing and its y variable is also changing as it's moving. The x is getting further away and the y is getting further away, and we might care about how fast the x is changing and y is changing, and that's what dx dt and dy dt would represent. X is this distance, y is this distance. Dx dt is about how it's changing, the x is changing, and dy dt is how fast the y is changing. So we'll get to that more later. So the derivative with respect to time of cosine of t, hopefully we feel good about all this stuff now. It's negative sine of t, and we don't need a chain rule thing because it's the same variable. Plus, here, 4t squared sine of x, there's nothing in between them, so this must be a product. These are multiplying times each other. And because when two things are next to each other and they are multiplying, we need to use the product rule. So it's the derivative of the first, and this is with respect to t, so I don't need any sort of chain rule thing. The derivative of 4t squared is 8t times sine of x left alone, plus, we leave the first one alone, times the derivative of the second one. But when we do the derivative of the second one, we're doing it with respect to t, and so this will need times dx dt. That's done with the product rule, so we did the derivative of the first times the second, plus we left the first alone times the derivative of the second, that used the chain rule, equals 15t to the fourth, and there's no chain rule here because dt is t there. So 15t to the fourth over there. Okay. d dt of sine of x squared plus cosine of t squared. The derivative of sine of x squared, the derivative of sine of something, is cosine of that thing left alone. The chain rule says we never change what's inside of a function. When it's an inside function, we then just do the derivative of the inside function. The derivative of x squared is 2x, and because we're doing it with respect to t, we need times dx dt. Here, the derivative of cosine of something is negative sine of that thing. We leave it alone, times the derivative of the inside, which is 2t, and we don't need a chain rule because it's the derivative with respect to t here. Oh man, that whole thing was off the page. Oh no, guys. Oh, that was so terrible. Hold on. You guys didn't see that at all. Well, I will repeat this and I'll just cut out this part of the video maybe. Okay, hold on. How am I going to fix this? Let's do it like this. So we're doing the derivative with respect to t here. And so here we've got sine of x squared. The derivative of sine of something is cosine of that thing left alone. The chain rule says we never change what the inside function is. We just multiply by the derivative of the inside function afterwards. So the derivative of x squared is times 2x. But because we're doing with t, we also need to do the derivative of x is dx dt. Equals the derivative of cosine of t squared. The derivative of cosine of something is negative sine of that something left alone, times the derivative of the inside function. The derivative of t squared is 2t, and we do not need a chain rule here because we're doing the derivative with respect to t. And so we usually simplify this to be 2x cosine of x squared dx dt equals negative 2t sine of t squared. That's how we'd write it. All right, last one over here. This is going to be the last one of these that we'll practice. d dt of this. And here we've got a and b as functions. So the derivative of a squared is going to be 2a times dA dt, plus the derivative of b squared is 2b times db dt, because both of these had a different variable than the one we were doing the derivative of, equals 0. Great. Now, let's talk about what some of these derivatives with respect to time mean. Create a situation that let's just say that fits. dA dt equals 4 feet squared per second. So here's this derivative with respect to time. You can see this per second. It's a rate. It's a rate. It's how fast something is changing. And it doesn't tell us what A is, but there's always this clue of like, what are the units? The unit is in feet squared. And feet squared is a measurement of area. So this is area. And so this gives us a really good sense that this A here is probably area. And so this means that the area of something must be changing 4 feet squared every second. And that just means like maybe, something is spreading out and taking more and more area. And so now we need to think of a situation that might be like making something take more and more area. Some examples would be something like a puddle of oil is spreading, oh man, that's not how you spell, is spreading at a rate of 4 feet squared per second. And that means every additional second, there will be an extra 4 square feet. You can imagine it as like in the classroom, those tiles are 1 square foot. They're all like 1 foot by 1 foot, the tiles on the floor. And so 4 square feet is like 4 of those square tiles at school. And so, there's something spreading that much. Could be something like a painter paints a wall at 4 feet squared per second. This is a rate. I should probably say at a rate of. And there are other things that could make the area of something expanding. We'll get to more examples later, but hopefully we see that there is this rate that area is changing. We could tell it's area because of the units, 4 feet squared per second. okay? So I want you guys to pause this and think for yourself for a second about what a situation might be for dr dt equals 40 centimeters per minute. Notice that it's a rate, and we have some units that gives us a sense of what might be happening. R is the variable that's changing with respect to time. So give it some thought, come up with something that you think this might be, and I'll give you some examples of what you might have come up with. So the units, this is a length. So there's something, or distance, a length or distance that is changing every minute. And 40 centimeters is about this long, something like this. Like about as wide as the page. The page width is about 40 centimeters. So there's something that's moving 40 centimeters per minute. Okay. I'll give you some examples of some things that might be right. Maybe let's choose something that starts with an R. Maybe it's like a roach is crawling at a rate of 40 centimeters per minute. So if a roach is crawling, it's moving, its distance is changing by 40 centimeters each minute. Maybe it's R as the radius of a sphere or something, like you're blowing up a balloon. As you blow up a balloon, the radius increases 40 centimeters each minute. So these are distances or lengths. The radius of a balloon is the distance from the center to the outside of the balloon, and as you blow it up, that distance is getting bigger because you're making the balloon get larger. As the roach is crawling, it's not where it is, it's how it's moving each minute. So when we look at rates, we're looking at like what are the variables and what are the units there, okay? Let's translate this into calculus. The volume of a cone is decreasing at a rate of 2 cubic feet per second. So using our knowledge from before, this is a rate. It's a derivative, okay? It's how something is changing. It's decreasing. And volume we'll usually represent with V. And so if we had something like V equals, this would be the volume of a cone is, but that's not what this is about. This is how the volume of a cone is changing. So it's changing. So we're going to need a derivative. And the way we write this is the volume of a cone is decreasing at a rate of, so this, all of this is dV dt equals the change in the volume over time, the rate that the volume is changing is 2 cubic feet per second. So 2 feet cubed per second. And a lot of times when we have this dt, you'll see the per second. The way we do cubic feet is feet cubed, and that's a measurement of volume. So a cubic foot, you know, whatever, looks like this. Okay, so a cubic foot. And so there's some cone that's getting smaller for some reason. You know, maybe it's because there's like a pile of something and, you know, the wind is blowing and it's getting knocked off. I don't know. Maybe it's something you put in the microwave. It was a cone shape, and as it cools down, it's decreasing in size. The volume is decreasing. Okay, but there's something not quite right here. It says the volume of the cone is decreasing. And if the volume of the cone is decreasing, it means it's going down. So the derivative, the rate, should be a negative rate. It should be negative 2 feet cubed per second. And so this says this. The volume of a cone is decreasing at a rate of 2 cubic feet per second. Okay. Now, let's get into the calculus and like actually doing some calculations with this stuff. Suppose x and y are differentiable functions of t. That means, so there's like, you know, where something is, the x variable and the y variable, this thing is changing over time. Like as 1 second passes, maybe it's over here. And as another second passes, maybe the thing is over here. And so both the x and the y are changing over time. And they're related by the equation y minus x 3x cubed equals 0. Find dy dt when x equals 1, given that dx dt equals 2 when x equals 1. Okay, this is all the information they're giving us, but what they're looking for is dy dt. Now, This is not y prime. This is not like find the derivative, solve for y and do implicit differentiation and find the derivative, because it's dy dt. dy dx is what we were doing last unit. But this is dy dt. It's the derivative with respect to time. Whenever you see this, what you just need to do, and this is fairly straightforward, is you do the derivative with respect to time on both sides. So what you're going to do is you're going to do implicit differentiation, but with d dt, the derivative with respect to time. And you'll end up with a dy dt and dx dt's. So the derivative of y with respect to time is dy dt. The derivative of x is dx dt. The derivative of minus 3x cubed is minus 9x squared times dx dt, because again, the variable we're doing derivative with respect to is time, not x, equals 0. And now it wants us to find dy dt. So guys, on these problems, they're almost always going to give you like everything you need except for one thing. So they want you to find dy dt. This is what we want to find. And they're going to tell us that dx dt is 2. So we're going to put in 2 for this. X is 1. Dx dt was 2. And so we can just substitute in and solve for dy dt. Dy dt is the only thing we don't know. We only don't know one of them. And that's to be able to solve, we need to only not know one of them. And we'll come up with tricks for what if we have 2 of them we don't know later. Minus 2 minus 9, x was 1, times 1 squared times 2 equals 0. So dy dt minus 2 minus 18 equals 0. And I can get dy dt by itself by either combining these and then moving it, or adding the 2 and adding the 18. Either way, dy dt equals 20. And this will be some sort of units per time. It'll be a rate with respect to time, but they didn't give us any units, so we don't need to worry about them too much here. The units are kind of important for this lesson. So hopefully you can try this on your own and see what you can do on this stuff on your own. Let's look at how this looks on the AP exam and how we can set this up. So here are some free response problems. It says, at a height h, the radius of a funnel is given by this. So this is the radius of a funnel. The units of r and h are inches, so this is measured in inches. We're going to use those units in a minute. The funnel contains liquid that is draining out. So this liquid is however high this is right now, and it's leaving the bottom. And so hopefully you can get a picture in your head that this water is going out. And so dr dt, the radius, is going to be how it's changing. And hopefully we can see that dr dt will be negative, and dh dt will also be negative, because both the height is getting smaller as this liquid goes out, and it's getting narrower as it goes down the funnel. And so the radius is getting smaller as well. So we can see dr dt and dh dt would be negative. That's just like looking at it. We're not actually answering the problem yet. The funnel is draining out of the bottom, has liquid that's draining out of the bottom. At the instant the height of the liquid is 3 inches, the radius of the circle, the surface of the liquid is decreasing at a rate of 1/5 inch per second. At this instant, what is the rate of change of the height of the liquid with respect to time? So in related rates problems, the tip-off that you're dealing with related rates is it tells you a rate, right? It's a rate of 1/5 inch per second. Here's a rate. They didn't even need to say a rate here. They could say decreasing at 1/5 inch per second, and seeing that it's a rate with time in it should tell you that it's going to be a ddt kind of situation. And it's even more specific here. It says, at this instant, what is the rate of change of the height of the liquid with respect to time? So I find it very helpful in these problems to identify explicitly, like just write down what are the rates it's giving you and asking for, and what are the variables that goes with them. We're going to start here with the rates, and we're going to find what variables we need that go with them. So let's see. The radius of the surface is decreasing at a rate of 1/5 inch per second. This is dr dt, where r is the radius. So the radius is changing at a rate of dr dt. And we usually use whatever letter makes sense. The dt will be there, but we'll use whatever makes sense for this. what is the rate of change of the height of the liquid with respect to time? Now, they don't give us so they gave us dr dt equals 1/5 inch per second. They don't give us dHdt, but it is a rate that is in this problem. And so we're going to start by writing it down. This is what we're going to be looking for. Okay, so we're going to be solving for it. Now, what is the variable that goes with this? Obviously, h is the height. And so in related rates problems, what we're always going to do is if they're looking for a rate, and they always will be, they'll be looking for a rate, we need to figure out an equation that will get us here. And the way we do this is we are going to write an equation. With these variables. And in this case, they gave it to us. They literally told us the equation was this. So r equals 1/20 times 3 plus h squared. And that's our equation with the radius and the height. And the way we're going to do this to get dr dt and dHdt is we're going to do the derivative with respect to t on both sides. We're going to do that implicit differentiation, and we'll get dr dt and dHdt, and we'll be able to answer this question. So d dt of r is dr dt. This is a constant multiplier, so it's just going to stay there. Constant multiplier times. This is a sum or difference. The derivative of 3 is 0. The derivative of h squared is 2h times dH dt. And now I've got my equation. I could simplify this if I want. And I think, I'm not going to. I'm just going to go ahead and plug in. Let's see. dr dt was 1/5. The h, does it tell us the height at the instant when the height of the liquid is 3 inches? So this is not saying that the height is always 3. This is a value of h. You can never, so I'm going to say this real quick. You can never plug in values unless solving, because h, you can't, so don't do before the derivative, because h is a variable that is changing. If you were to plug in 3 here, it would make it look like it was a constant, and then the derivative would just be 0, and it would look like the radius is never changing, but that's not right. Now we can plug in h as 3 because we're plugging in to solve for what dHdt is. And so let's go ahead and multiply this. 1/5 equals, so 2 times 3 is 6. This is 6/20. And I could simplify that to be 3/10. I'm going to divide by 6/20 on both sides. Dividing by a fraction is multiplying by the reciprocal. So this is dH/dt. And so dH/dt is equal to 20/30, which I can divide by 10 and divide by 10 and get 2/3. Okay, now I should say what the units are. dH/dt, the height, what is it being measured in? Height is being measured in inches. It said h is being measured in inches. And the time is going to be whatever it said here. The time is being measured in seconds. So it's 2/3 inch per second. So let's see what this actually means. What are we actually talking about here? Well, we had this specific part of the water, and at the instant when the height was 3 inches, so when this was 3 inches high, we found that the height was, something is wrong here. Oh my God, guys, I made a mistake. Who can tell me what my mistake was? It has to do with the value of dr dt. dr dt is not 1/5, and so my dH/dt is not 2/3. What is wrong here? Well, the liquid was decreasing at a rate of 1/5, and so dr dt should be negative. And so throughout here, this is going to be negative, negative, negative. It will make this negative and this negative. And this should make sense that dH/dt ends up being negative because the water is draining out, and so the height needs to be going down. So that's a little double check I was doing on myself there to think, did it make sense at the end? And it caught my error. So when the height is 3, as the water pours out, it's going down by 2/3 of an inch each second. Now, as it goes down further, that rate might change. This is an instantaneous rate of change. Oh man, I remember grading this problem. So I was at we were in Kansas City, I think, was where the AP grading was this year. And we were grading this tree part problem. This was one of the ones I was grading. And there was some things some kids missed. Okay, so let's look at the height of a tree in meters can be modeled by the function g, given by g of x equals 100x over 1 plus x, where x is the diameter of the tree. So it's saying that the height of the tree is related to the diameter of a tree. So how wide a tree is can tell you about how tall the tree is. Okay, I believe that. Okay, when the tree is 50 meters tall, so it's like going to be 50 meters tall, the diameter of the base of the tree is increasing at a rate of 0.03 meters per year. Now, this should be your tip-off right away that this is a related rates problem. Why? Well, it tells us it's a rate. We've got meters per year. And so this is, what was the diameter of the base? The diameter is x. So this is, I always like splitting it up into rates and variables that go with those rates. The rate is dx dt. It's the x is the diameter. This is the change in the diameter. The diameter is increasing at a rate of 0.03 meters per year. Okay. What is the rate of change? So what variable must go with that? Well, x. Okay. What is the rate of change of the height of the tree with respect to time? So the height of the tree with respect to time, and the height was g. So this is dg dt. That's what it's asking for. Equals question mark. And so we need, g or g of x, whatever, is what's going to go with that. Okay. And look, we have a formula between g and x. Great. At the time when the tree is 50 meters tall. Okay, great. So we're going to use our function g of x equals 100x over 1 plus x. And we're going to do the derivative with respect to time on both sides, because we need to get to the place where we can actually get these rates. We're looking for dg dt. To get dg dt, we need to take the derivative with respect to time on both sides. So the derivative of g of x with respect to time is dg dt. dg dt equals, now how do we do the derivative here? Well, this is a quotient. We need to do the quotient rule. It's the derivative of the top. The derivative of 100x is 100, but be careful, it's the derivative with respect to time. So it's 100 times dx dt, the derivative of the top times the bottom left alone, minus, we leave the top alone, times the derivative of the bottom, the derivative of 1 plus x, the derivative of 1 is 0. The derivative of x with respect to time is dx dt over the bottom squared. And now let's see if we can plug in. So we're looking for dg dt. This is what we want. And we know dx dt is 0.03. And do we know what x is? Well, no. It did not tell us what x is. X is not 50. 50 is the height of the tree, right? So the tree is 50 meters tall. G of x, be very careful. This is, I wish they had used height. Honestly, a lot more people would have gotten this right on the AP exam if they just used reasonable variables instead of using g of x, g and x. If they'd use like h and d for the diameter, if they'd put like h of d equals 100d over 1 plus d, it would have gone a lot better for some kids. When I was grading this, there were a ton of kids who plugged in 50 here, but that's not right. We want to plug in x. X is the diameter. They told us that g of x is 50. And so sometimes they won't give you all the information you need, and you need to go back to the original equation, because this is a relationship between the height, this is the height, and the diameter. And so we can plug in the height they gave us to find. We need to plug in what x is here. I guess we can also plug in 0.03 here. We need to find what x is to be able to plug it in to solve for dg dt. So they gave us that the height was 50. And so we can plug it in and solve this equation to solve for x. Go ahead and solve that. And hopefully you knew that when you're dividing, you need to multiply to cancel out the dividing. So we're going to multiply by 1 plus x. And that is a binomial, so we should put in parentheses. The 50 will distribute to both. And we get 50x plus 50 equals 100x. We can move the x over to the other side. 50 equals 50x. Divide by 50, x is 1. And so x here is 1. They didn't tell us that in the problem, but they told us the height, and we can go solve for x because they gave us a relationship between the height and the right. So let's look at this. I will tell you a trick on the AP exam that's nice is you don't actually have to simplify. You can leave your answer as 100 times, was this increasing? Yeah, increasing, so positive 0.03 times 1 plus 1 minus 100 times 1 times 0.03 over 1 plus 1 squared, and leaving it like that gets you full credit on the AP exam. Now, you might not like how that looks. It's a little bit ugly. So let's see, 100 times 0.03 is 3. It moves the decimal to the right by 2 places. And 3 times 2 is 6. 100 times 1 is 100. 100 times 0.03 is 3. So 6 minus 3 over 1 plus 1 is 2. 2 squared is 4. And so we get 3/4. So dg dt equals 3/4, although you also could have left it like this and gotten full credit. If you're not comfortable with your ability to simplify, don't. Okay, but you need to make sure you're writing it. Okay, last one. This will be our last one for today. At the beginning of 2010, a landfill contained 1,400 tons of solid waste. So, I don't know, there's a big pile, 1,400 tons. Now, is this a rate? No, it's just an amount, tons. Now, if it said tons per minute and something was changing, that would be a rate. This is just an amount. The increasing function w, so w is always increasing, models the total amount of waste. Okay, so they're just like dumping more stuff into the dump. It's increasing. Models the amount of solid waste stored at the landfill. Planners estimate that w will satisfy the differential equation. We'll talk about this. You'll learn about it more later. But for now, a differential equation is just an equation that relates to, that has a derivative in it. So this is a differential equation because it tells you a derivative is equal to something. We'll have a whole unit on differential equations later. This was actually part of a differential equations problem. So if you're like a little confused by the differential equation part, don't feel bad about that. That'll come up later. So the waste will satisfy this. Now this is an equation that's telling you about the rate of change of the waste. The rate of change of the waste with respect to time, so how much the waste is changing over time, is 1/25 times how much weight is there minus 300 for the next 20 years. Okay. W is measured in tons and T is measured in years from the start of 2010. Use the tangent line to the graph of W at T equals 0 to approximate the amount of solid waste in the landfill contains at the end of 3 months, which is time equals 1/4. 3 months is a quarter of a year. T is being measured in years, so T equals 1/4. I was actually very thankful they put this on the AP exam this year, on the year they put this one on there. I think a lot of kids would have put like 3 was time there instead of 1/4, so they were very kind there. So we need to use the tangent line. How do we create the equation of a tangent line? Well, we need a slope, and we need a point. It's at time equals 0. So time equals 0 means no time has passed since 2010. And so what is the point? Well, the point is going to be 0. So no time has passed. How much waste is there at time equals 0? Well, it says it started with 1,400. So the point was 0, 1,400. The slope is going to be, we can get from the differential equation, this is the derivative, it tells us the rate of change. So dw dt at 0, 1,400. So the derivative when the time is 0 and the amount of waste is 1,400 is 1/25 times w is how much waste there is at 0, and that's 1,400 minus 300. And so that's 1,100 over 25. And this is on the no calculator portion of the exam, by the way. This is like one of the nastier calculations they had you do. You should know that for every 100, there will be 4 25s. So like 100 is 100 divided by 25 times 11. So 4 times 11 is 44. It's the easiest way to do it. You could do long division. I mean, you could do it like this. But it's a little bit easier just to be like, oh, 25 goes into 100 4 times. 4 times 11 is 44. So dw dt equals 44. And so what is the what is the equation of the tangent line? Well, the amount of waste is going to equal, I guess we could say y equals, fine, y equals, the amount of waste is going to equal the slope, 44, times, the point was 0, so t minus 0, or x minus 0, plus, I guess I should put a t here, plus, what was the original amount? 1,400. So it's saying, okay, look, the amount of waste we started with was 1,400, and it's going up by 44 tons each year right now. And so we can use a time of 1/4. We'll plug in 1/4 here to estimate about how much waste there is. So a fourth minus 0 is a fourth. A fourth of 44 is 11. 11 plus 1,400 is 1,411. Now, we're going to skip this one, guys. Sorry, there's this whole section that we did. I skipped 2 lessons earlier in the year to try to make up some days we lost. Don't worry about number 15 for now. We'll be talking about underestimates and overestimates in about a month, a little less than a month. Okay, guys, have a good day. Hopefully you feel good about these related rates. Remember, the big idea is just that, like, sometimes there's a relationship between how fast the tree is growing out this way and how fast a tree is getting taller. Sometimes there's a relationship between how the radius of a funnel is changing and how the height of that water is changing. These quantities, the way they are changing is related to each other. And we will get into a ton more situations on like what kinds of things might be related to each other. But the big idea is that we're using the derivative with respect to time to do implicit differentiation on both sides and find the relationship between these rates. Okay, so good luck. I hope your homework helps you practice this stuff some. And any questions that are about using the second derivative to talk about underestimates or overestimates, we will of course be getting to later this year, and you can skip for now. Have a good day, guys.